Have you ever wondered what happens to all those tiny plastic particles once they enter our rivers, lakes, and oceans? Where do they go, and what forces guide their journey through these vast water systems? The distribution of microplastics in water bodies is primarily driven by a complex interplay of physical forces, the inherent properties of the plastic particles themselves, and biological interactions. These factors dictate how microplastics travel, settle, or remain suspended, influencing their ultimate fate and environmental impact. Understanding the why behind this distribution begins with the physical characteristics of the water body. Ocean currents, river flows, and wind patterns act as primary transport mechanisms, carrying microplastics over vast distances. For instance, large ocean gyres, which are massive circulating current systems, can accumulate significant concentrations of plastic debris, forming patches like the Great Pacific Garbage Patch. In rivers, the velocity of the water, influenced by factors like discharge rates and channel morphology, determines how quickly microplastics are transported downstream and where they might settle in calmer areas or floodplains. Additionally, atmospheric deposition, driven by wind, can introduce microplastics directly into water bodies from land or air. Particle properties also play a crucial role. The density of a microplastic particle relative to water is a key determinant. High-density plastics, such as polyethylene terephthalate used in beverage bottles, tend to sink, accumulating in sediments on the seabed or riverbed. Conversely, low-density plastics like polyethylene, commonly found in plastic bags, can float on the surface, making them susceptible to surface currents and wind. The size and shape of the particles further influence their movement, with smaller, irregularly shaped fragments being more easily suspended and transported, while larger or more uniform particles may settle faster. The surface chemistry of the plastic also dictates how easily it interacts with other particles or organic matter. Furthermore, biological processes significantly alter microplastic distribution through a phenomenon known as biofouling. Microorganisms like bacteria, algae, and fungi can colonize the surface of microplastic particles, forming a biofilm. This biological growth increases the overall density of the particle, often causing even traditionally buoyant plastics to sink. This process can transform the vertical distribution of microplastics, moving them from the surface waters down to the benthic zone, impacting different ecological communities. Biofouling changes the density and surface characteristics, turning what might float into something that sinks, altering its journey through the aquatic environment. This comprehensive understanding of how physical, chemical, and biological factors orchestrate microplastic movement is essential for accurate modeling and effective mitigation strategies. Recognizing the roles of ocean currents, particle density, and biofouling allows scientists to predict accumulation zones, assess ecological risks more precisely, and develop targeted interventions to protect our aquatic ecosystems from this pervasive pollutant.
If you love learning about water, like, subscribe, and keep exploring with us.